pleasure today that we have Professor Mauricio Terrones coming from Pennsylvania State University. Mauricio is kind of my old friends, kind of dating back to the kind of many research in the nanotubes, and graphenes, and 2D materials, and all the way we share the very the kind of similar path. Mauricio did the undergraduate study in Iberian American University in Mexico, and then do the PhD in the University of Sussex. They're working with the Harold Porter, right? I think, yeah, and that's where that started. Now this kind of involving the carbon nanostructures. Ever since that, he has done a lot of exciting work in the many low-dimensional nanostructures, including graphene nanotubes, 2D materials. He's been in the very broad in terms of research. I think his affiliation is in Department of Physics, Chemistry, Department in Material Science, and what else?
No.
And as you see that he's been doing a lot of exciting work in the synthesis, characterization, and look at this various different interesting phenomena in these nanoscale materials. And today we are going to hear about some of the research development of the stuff. All right, there we go.
Thank you. Thanks. Thank you very much, Philip. Thanks for the invitation, and thanks for joining. I hope so the sound is good, right? So you can hear me, people that are remote, right? So, okay.
Yes, you sound great.
So, thank you very much. So today I will talk about some of the things that we have been doing recently regarding transition metals like carbonides, 2D materials. I will tell you a little bit of the carbides, very thin, ultra thin carbides, not much things, ultra thin carbides, and some of the things that we're working on. And I would just go through with different types of, defects and how we are able to control, to a certain extent, these defects. First of all, I have to say the talk, it will be not very carbon-like, because I'm a carbon scientist originally, so just Philip also started with carbon. And I'm the editor-in-chief of a journal that is called Carbon. The impact factor is 11.3. And but if you want to know about carbon, or you want to submit your papers to carbon that are related to carbon, right? You can submit it to this. And we usually write a perspective. The editors, we write a perspective every 2 years on what is the current research and challenges carbon. So this is an open access paper, but if you want to know a little bit what we think in the area of carbon, then you can access that. So that's it regarding carbon, and I will switch. So as Philip mentioned, well, my home department is physics, but I also have course appointments in chemistry and material sciences, and I have students from the three different departments, and sometimes that's very good because that enriches, that sort of creates a very nice environment and forces students to talk the same language or to manage to communicate different things or same things in different ways, which is closer to real life. And this is the barbecue we had at home, and then we have students. We have small members. They are not part of the group, but this is Diego, my son, and this is my dog. But yeah, that's okay. So this is some of the work. We have PhD grad students. We have visiting scientists, research associates, postdocs, and these are people who are doing the work. And I will present some of the work that they have done. So I just wanted to show you the names. And we know, very well, the area of 2D materials started with graphene, right? So, and then in 2010, there was this paper by Infite Mag, Jishan, and Tony Hines about the exfoliated monolayer of molybdenum sulfide, and that you have the very sharp photoluminescence here when you have a monolayer. And here the explanation is, of course, you have an indirect band gap that happens in the bulk for molybdenum sulfide. But as you reduce the number of layers, the direct band gap at the K point becomes very strong, and that's why you see that speaking the photoluminescence. So that's very interesting, because that means that if you have monolayers of these materials, semiconducting TMDs, then you would see a high photoluminescence from these systems. And we're taking advantage of this. At some point, I will show that some bio applications as well regarding this. But so today I will talk about the defects in TMDs. And let me just classify the defects in this transition metals like I told you. I will classify them by dimensionality. I mean, of course, I mean, we can classify them in different ways, but I will call it zero-dimensional defects to those defects that include vacancies or add atoms, right? So you create a vacancy, you can remove sulfur atoms, or I mean, chalcogen atoms or metal atoms, and you can have substitutional doping. That means replacing the metal, replacing the chalcogen. So you have this sort of defects, these point defects, or you can have these structural sort of defects that are square-like or octagon-like defects that will provide curvature to the system. So it's similar to the pentagons, what they do to graphene. They create curvature and you can create a fullerene. In this case, you could create cages eventually, or you can, you know, create some negative curvature with the octagons. Then we have, I call this 1D defects, so which could be the edges of these systems, right? So you have, for instance, edges of ribbons or edges of crystals. You have also grain boundaries, right, where you can just join. In this case, you are pushing the octagon and square-like defects here in a row, and then that sort of counterbalances the angles, and then basically you create this boundary. Or you can have stacked in-plane heterostructures, which is stitched monolayers, and then you have one material here and then one material there, and then you have one big channel here. And then you have the other, which I call these 2D defects, but it's basically whatever you can think of 2D, which goes from the van der Waals solids to rippling or scrolling or wrinkling or folding. And the nice thing about 2D materials is that you can fold the 2D material, right? It's the only thing that, I mean, the only system that you can fold, and this folding will provide some high strain locally. And if you take advantage of folding, also you can find interesting physics behind that. So I will go through with a few of the ones that we have been working recently, and then I will show you some of the things that we have done. So I will go with the substitutional doping. So that means in situ, or in the synthesis, we replace the atoms, and then we try to dope or to make an alloy of the system. So I will go through with how we do it, and it's a very simple way to do it. So the idea of the synthesis that we're applying is that synthesis method that people can try everywhere. I think the field advanced very quickly in the area of TMDs, also with graphene. When people were able to grow graphene with CVD, that was a big thing, right? Because everyone could grow. I mean, of course, Scotch tape, mechanical exfoliation was also easy. In the area of TMDs, besides the mechanical exfoliation, the way to do it is just basically you vaporize sulfur, you have an oxide of moly or tungsten, and you just heat it, and then you get the monolayers next to a substrate that they grow. And it was very easy to make. So I think that sort of opened up lots of things. What we are doing here is a little bit different, but the point here is we want to introduce specific atoms in the lattice, the TMD, and you will see that you can basically, we have some control of where we can place these atoms as well. But the way to do it is we develop this in the group, and then the idea is just to use a liquid phase precursor. Basically, what we can have a precursor for the metal, which is moly or tungsten, and we can have also a precursor of the dopant or alloy that we want. And we just mix them in solution, so it's sort of chemical way. You spin coat it here, and you put it in your substrate, and you vaporize sulfur or selenium, and then you would get the doped system, right? So in this case, I'm showing here, you have vanadium dopant here, you have moly and tungsten, and then you have vanadium, right? So you can try different things, and again, depending on this in this particular structure, you have moly-rich area here. And then you tungsten rich outside. So you can create some sort of interfaces as well. But the whole point is, in this way, we can introduce the atom you want to dope with, or the atom you want to make an alloy with.
Yes. The previous one that To get this spatially separated one, basically you have the two-step process.
No, it grows at once. Yeah.
But if I spin core, then how do I know that which part is more efficient is which part?
If you use your moly precursor, your tungsten precursor, it's just given by the kinetics of the reaction. So the moly will start, condensing first, and that grows first. That's a seed, and then tungsten takes longer to, takes higher temperatures to have them. So that's why you have, and again, you have these nucleation sites are usually defective areas, defective points in the substrate of silicon oxide. But we are finding even more interesting shapes that I can show you. So for example, let's do some, so we did some work with rhenium, right? So in the case of rhenium, we use the precursor of rhenium. So this case is moly sulfide, right? So we use ammonium heptamolybdate, so that's the rhenium precursor, and then we have the sorry, this is the moly precursor, and the ammonium pernate, that's the rhenium precursor. So basically, you mix these two, and then you can mix them with different ratios by weight, and then you end up having either rhenium atoms that are in the lattice here, right? And you have, or you can have a rhenium, so rhenium disulfide interface of 1T prime rhenium disulfide and the 1H or 2H molysulfide here. So you can have, depending how much material you put, how much rhenium you can have like more doping, or you can have these sort of sharp edges with the rhenium and the moly. And then you have this growth of these triangular systems. One thing we did was with vanadium. The reason why vanadium is very interesting is because we can dope. We can dope and we can alloy with vanadium. We can start with 0.1% of vanadium, but we can go all the way to 15% vanadium. So that gives us a very long range, and we can start monitoring the properties as we introduce vanadium into the system, and that's what we did. So in this case, we use ammonium tungstenate, which is the tungsten precursor, and then this vanadium sulfate, which is the vanadium precursor. So we use both. We use the system that I showed you. We vaporize, and then we can see the signal of vanadium here by EDX. But what is more interesting is that we have here some examples that we have 0.4 atomic percent of vanadium. We can have 2% of vanadium and 8% of vanadium. I selected these because they are representative, but one thing, these are not vacancies, these are vanadium atoms, but they are lighter, sort of the very light Z contrast. And one thing that I want to show you is that in this case of the medium dope, you can see the average distance between the vanadium atoms is around 1 to 2 nanometers. When it's 8%, basically you have clusters of vanadium and they're very close to each other. So I just want you to remember that, because that might change the properties of the systems that we're seeing. But this method, so in principle, so we can put different concentrations, we can start studying the systems. So I just go quickly, because I don't have much time, but this is the pristine tungsten disulfide, right? This is the Raman spectra of the pristine tungsten disulfide when it's in resonance. So this is when it's with the green light, this is with the blue light, but the green light this is resonant. The 2LA mode here, it's resonant. This is the LA mode here. But then you have the E prime mode, which is the in-plane mode, and this is the out-of-plane mode. This is silicon. But you can see as we introduce vanadium with lightly doped, medium doped, heavily doped, you can see that this resonant peak becomes basically, it decreases rapidly, and the photoluminescence also we can see as we increase vanadium, we start seeing a shift towards the lower gap, right? So basically when we put vanadium, so the gap is reducing, and that's something we're seeing. And of course, if you put too much vanadium, then basically the PL also it's been inhibited because you have many defects there. So, but you can see we're doing something, and then we are really seeing this in PL and even in Raman spectroscopy. So that means that the properties of the material have been changed. And this is something that, so we made some devices, and with this, and this is usually it's an N-type material when it's not doped. But when we start doping it with vanadium, we start to see that the P branch starts to develop, and it sort of becomes close to an unbipolar system. But again, that shows you that with different samples and different measurements that we did, we saw more or less the same trends. But what was more interesting was the magnetism here. And this is something that we still need to do some more work. I mean, this is room temperature. We do these VSM measurements of the substrates, and we sort of, I mean, we subtracted, of course, the substrate, and one thing we did, we saw this is we left the magnetic signal from the substrate here. We have the pristine system, which is basically there's no ferromagnetism, but then the 2%, the 0.4%, you can see a little bit of hysteresis loop. 2% is when we see the highest hysteresis, and the 8% we see basically none. So you remember that the space in between, the average space in between the 2% was around 1 to 2 nanometers. So if I go here, the interesting case was here, but also this is interesting when you have this clustering of vanadium atoms. So it was something that we could see a ferromagnetism, and then we didn't see any ferromagnetism. And this was interesting. We could see even, this is at room temperature, this is a coercive fields, so that we have, in this case, we have coercive fields around 130 oesters, and a lower temperature we have a bit higher, right? Then the first time I saw this, I said, well, it cannot be. I mean, this might be an impurity, it might be something else, and ferromagnetism is very difficult. And then another student did a similar experiment in a different furnace with tungsten diselenide and vanadium. And it was a different setup. So we didn't use even this technique. So what they found, well, let me just, so what they found in the tungsten diselenide, it was similar thing. So he did the same set of, vanadium concentrations were similar ones, and then we could see that ferromagnetic signal was high when in this case it was 4%, but I mean, it was basically, you can see the distance, the vanadium, average vanadium distance, it was sort of similar, and then we could see the ferromagnetic signal, and as we put more vanadium, that ferromagnetic signal was dying out. So the fact that when we put more vanadium, we couldn't see any ferromagnetic signal was very interesting, because you could see it's coming and it's going. But again, I think we need to do more measurements, but one possibility is that, and then it depends how apart you have the vanadium atoms, is that when you do spin polarized density of states, depending how far you have the vanadium atoms, you have them apart like 1 or 2 nanometers. Basically, you can align the spins. When you apply a magnetic field principle, you can magnetize them. But when they are becoming closer to each other, then you have an antiferromagnetic contribution. So basically, when they are very close, they cluster, and then all this ferromagnetic contribution is going away, and when it's near, basically you have this spin polarized. It's not. So this could be a model for this, but again, we are trying to do some optical measurements that we could see this ferromagnetism. Again, this is room temperature. What we're seeing this in tungsten diselenide, tungsten sulfide, moly sulfide as well, and moly selenide. Everything we have tried with vanadium has worked. So again, but it's an interesting phenomenon. We want to understand a bit more. There's a Korean group, I think Yongki Lee is doing this with tungsten diselenide. They saw something as well. It's an interesting system. They did some MFM. We did MFM, but I don't believe on the MFM data. But anyway.
Do you have some estimations of the purity?
Yes, it's 470 Kelvin.
470.
Yes. But again, I think it's an interesting system. But again, the fact that you can put more vanadium makes you think, okay, if the medium vanadium gives you ferromagnetism and the other one doesn't give you ferromagnetism, then that means that we're doing something that we can reproduce. Okay, so that's with the vanadium, and that's something that we're doing. We're also trying with iron. So, but this is just the way the system works. So you can see the precursor of tungsten when there's no iron chloride. When you put a little bit of iron chloride, you get the suspension. This is the one that you spin coat. And when you put more concentration, then you can see more yellowish color. This is the one you spin coat, you do your reaction, and you have iron doped that is 0.7% or highly with 2.8. Vanadium is very particular because vanadium you can put it all the way to 12%. Here, this is the limit that you can have. And again, you can look at the properties and you can look at, but in any case, we're trying out, we're doping out with erbium, with deuterium, which is, maybe these are interesting systems, but if you have ideas, we can try to do it. Okay, so now regarding the shape and how these dopants affect the growth, that's going to your question, is that you can have different shapes, and that depends on the sulfur. One of the things might be the sulfur chemical potential. So you put lots of sulfur in your reaction, you tend to create these triangular lattices. If you put less sulfur, you get this hexagonal lattice. But there are other parameters besides when you put another element there. And this is something that we have seen with the iron and the tungsten. So you have a hexagonal or close to a hexagonal monolayer where you have photoluminescence everywhere, but you have bright spots here and you have darker spots here. So, and one thing that we notice is that the bright spots have almost no dopants, and the dark spots will have more dopants. So you have more iron here. And this is with the low doping case. In the high doping case, the same. So you have the darker spots have more iron. So basically you are doping with iron, or you're alloying with iron here. And then you have this growth in these hexagonal alignments. The hexagonal alignments, the interesting thing is the termination of the edges. So when you do the edge termination, so if one edge is, these are zigzag edges. So if one edge is, it's metal terminated, the other edge will be sulfur terminated. So it's metal, sulfur, metal, sulfur, metal, sulfur. So one thing that we found with theory was that the tungsten atoms, they prefer to go to the metal terminated edge. And the sulfur terminated edge, what happens is that that tends to create sulfur vacancies. So there's more like metal vacancies. So the metal vacancies are more likely to be created in the sulfur terminated edges. So that means when you have these metal vacancies, that's very suitable for putting the other dopants. So what happens during growth is that preferentially the dopants go to these sulfur terminated edges, and this alternates every other phase. And that's our explanation for finding. But I think the nice thing here is that, and we have seen it with other systems, is that with chromium as well, they tend to go to the dopants tend to go to the sulfur terminated edges. So you can control where you want your dopants in that case. And again, here, in order to get the hexagonal shape, we played a little bit with the sulfur concentration. We played with less sulfur concentration, so we could have the hexagonal lattices. Again, this is, we're working on this, and in principle, if you control the dopant, the sulfur concentration, and where the dopant is going, and temperatures, you could in principle get this beautiful structure as well. These are made of tungsten disulfide. And then these are monolayers. And again, here, in this tungsten disulfide, you have very sharp photoluminescence here. You have here you have a very bright edge. So these are twin boundaries, and you have darker here, which is basically, these are more vacancies that we have. So, but these stars have been made. And in here, we play a little bit with the tungsten concentration, and we play with a little bit of the moly concentration. So we're playing with different parameters, but in principle, we can control the growth of this. I mean, we're working now on this and trying to understand the growth. But here, in the case of the stars, you have one peak of the star is, let's say this is metal terminated, the other peak is sulfur terminated. Metal terminated, sulfur. So that's what we have here in the star shape.
So this shape is controlled by the controlling the volume to sulfur ratio during the growth. Is that
And use that's right. And using low sulfur concentration. Yeah.
How do you actually do that? Basically, sulfur you have the precursors and the chip just kind of.
We put less sulfur in the system. I mean, with less sulfur powder, or you can do it with H2S as well.
I see.
But yeah, I think that's a very good point. So the way we found it is that we started finding. I mean, it took us like 1.5 years to find what was the reason, right?
Yeah.
We could see some stars. And how can we make more, right? So I told the postdoc we had to make more. Like, no, they cannot, not reproducible. And then we found some moly in the core. And then we started putting moly, a lot of moly, and it was not working. So I said, let's go to the. So in the end, we need to add like very small amounts of moly. But it's now it's reproducible, so that's why we can have this.
So you get this with moly.
It's tungsten mainly and a little bit moly.
So there are 3 parameters: some small amount of moly, tungsten, and then contents of.
Sort of like sort of like magic, but yeah, that's.
Beautiful stuff.
But it's
We have an explanation why the field is stronger.
I can explain, for example, the ones here. I mean, we have looked into high resolution PM, right? So we have here, we have some extended vacancies for the material. So they basically the stitching is not very good. So we have vacancies, and that creates this dark lines. Here we have twin boundaries. And for some reason, we need to understand why these twin boundaries produce this. And here, this region is that we believe we have very high concentration of tungsten. And here we have a little bit of moly. So, but again, it's on the works, but it's just to show you the potential. They look nice. That's it. Okay, let me just move on. The next thing is it's trying to grow to understand the vacancies, and this is more for. Is there a way you can measure the number of vacancies that you have in the system if you do some spectroscopy, right? So we tried the Raman spectroscopy for that. And then we did this work of using gallium ions, and but you can do it with any type of ions. But so what we did is we deposited on a quantifoil grid. We deposited the crystals, and in the same crystal we could do Raman before and after the irradiation of gallium in the same triangle, right? So we did many measurements and observations. Because what we wanted to measure is what is the distance, the finite crystal length here between the defects. Not the defect to defect distance, is the crystal length. And so one thing that you notice when you start putting this is your ions, right? This is the pristine, you have the in-plane mode, the out-of-plane mode. And you start to see that the LA band starts increasing when you do the when you introduce more defects. And then these are vacancies of sulfur, these are vacancies of the metal. So one thing is if you plot the intensity of the LA mode with intensity of one of the other 2 modes, the in-plane or out-of-plane, you get straight lines. And this is something that, so we measured this and we quantified also with TM. So this shows you the different magnifications of the treatment. So the pristine one, this is PMMA that is used for depositing, and then you use basically you can see the vacancies, and you can see how damaged the sample can be, right? So one of the things that we did, it's other papers they have used for graphing, they have used the defect to defect distance, but that doesn't work when you have too many defects or when the defects coalesce, right? Because then you have a larger hole, and it will give you what is the defect to defect distance. So what we did is the finite the final crystal length here. So we define this, and then with different eyes, we define the final crystal length. So we measure this experimentally and then we just plot it here, right? And this is basically the mean final crystal length with the ion dose, and we can then correlate with these formulas the intensity of the LA and the E prime peaks. So if you know the intensity of the LA peak and the intensity of E prime peak, or the A prime peak, then you can know the final crystal length if you use those formulas. For tungsten disulfide, we have a similar thing. It's similar equation, but it's not the same values. But one of the things is that it's the final crystal length. So this is a good crystal, right? So this has very less defects. So in this regime, but if you have too many defects, then you are in here. So so that's something that it can be used for predicting how defective your system is before even you try to do anything with it, especially with CVD grown materials. So one thing we did is we did afterwards. So after we irradiated, we then annealed it in H2S. So we tried to anneal it. We passivated with H2S. And after irradiation, then we could see that some of the defects annealed, and we can see the recovery of the PL coming as well. So the irradiated one is the PL, but the annealed one is sort of have a PL that is being recovered. So you can anneal the defects as well. So maybe a way to process even a sample that you want to anneal defects, you can just put in H2S and have it more perfectly, and that's the way to do it. Let me go just quickly with the applications of this fluorescent monolayer. So you know they are fluorescent, so they can be used as biomarkers, right? So what happens is if a cell ingests this, they can start fluorescing, and they can monitor where the cells are. This similar to a fluorescent biomarker. So what we did is we use the tungsten disulfide. We have these cancer cells, and what it was surprising is that when you put a cancer cell on top of this material, the cells start digesting the material, and they start fluorescing. And then we did some work on this. So basically, you put you grow your material, you put it on substrate. In this case, we put it on a glass. I mean, a silicon quartz, sorry. And then you have the triangles here, and then you have the cells here. You put them then the cells, and you can see the cells are on top of the triangles, and you can start to see the fluorescence after some time. So you can see the cells having the. But it was interesting because we said, okay, how much material, how is the ingestion happening, and then we did some TM and PL before and after digestion. So this is the PL. So this is the material, the pristine material, and this is after the cell has ingested the materials. We have more extended defects that have happened, right? And then you have this sort of tears from the cells sort of tear apart these fragments, which are very tiny, right? So this scale bar is 30 nanometers. So these are triangular ones, like eating Doritos, right? So the cells were, but I think that what it was interesting, it was, of course, we tried to do cross sections of the cell, and we tried to find the fragments, but they are too small, we couldn't find it. But one of the interesting things was that this is experiment. So before, there are no cells, there are no fluorescence. After 4 hours, we can start seeing the fluorescence. And after 48 hours, we see the fluorescence even higher. We still don't understand why this is happening. But one thing that is happening is that the cells are dividing, like when you can have third generation cells, second generation cells, third generation. And what was interesting is that after generations, the cells were still fluorescent. So how can this be used? I mean, one way, if you have very tiny fragments of molysulfide, can you internalize these fragments in a virus? If you can internalize these fragments in a virus, and you can make the virus fluoresce, then you can maybe see how the infection happens specific virus and specific cells and how you can monitor the infection, right? So that would be one way. But again, this is interesting. And then you are thinking about quantum dot sort of regime on this, but I think it's interesting. And what is also interesting is just with the spectroscopy before and after, and then we can see that, of course, use silica, we will have a signal. The tungsten disulfide, you have the A and B exciton. The cells after ingestion, you have also the excitons here, so the cells were and again, this is the cell viability. So the cells, this type of cells in time, they were not dying because of ingestion. So this is, again, this is interesting. Okay, so now let me switch gears and talk to you about, I talked to you about a bit of defects in TMDs, and let me tell you a little bit of carbides, and I was discussing with Philip this morning. These were something that we put in the proposal with Susan Sinnott originally, that we can make molycarbide and molysulfide, but the carbides is not a layer material, so it's a bulk material. So how can you thin it all the way? And again, you get into the Maxine idea. But what we wanted to do is, can we have heterostructure of carbides and sulfides, or carbides and selenites, and this is something that we did. So the way we grow the carbides, and this is alpha molycarbides, it's very simple. So you use, in this case, you use copper and moly. This is silicon oxide. You use copper and moly foils, and then you just flow methane with argon oxide. And then, so you have the copper molten in the moly, and then you have the growth of the carbide, and then you can just remove that. And then what you get is very thin carbides. These are beautiful. This is moly alpha carbides, and you can see these beautiful shapes. And there are monocrystals and very thin. So it could be these ones are embedded in the copper, and you can see it could be as few nanometers, and could be large, right? So several microns length. So what we did is, so we can grow these carbides. What can you do with carbides? So yeah, it's just to start sulfurizing or alkogenizing the carbide, so we can start making these heterostructures. So what we did is we passed through H2S gas, right? And we started to see interesting transitions that I can show you. But so this is the pristine molycarbide, which is alpha molycarbide, is very well known. So this is, you have these hexagonal platelets. You have this XRD, and there's no Raman with XPS. And then after 5 minutes of sulfurization, we could start seeing molydisulfide, and we can see clearly molydisulfide, and we can see the molydisulfide in all these characterizations. So in this case, we're growing molydisulfide on top of the molycarbide. So here is the structure of, this is the STM structure of alpha molycarbide. This work was done in collaboration with Eric Hudson. And then here we can see it's sort of a moire pattern of the molysulfide on top of the molycarbide. And this is what we see. So let me go through the experiment and show you what happens with different types of sulfurization. So we use pristine 1 minute, 5 minutes, and 20 minutes, and we sulfurize. So we started to change the alpha molycarbide, and here we see the alpha molycarbide, the pristine one, and then we can just index this, and it's very nice monocrystal in molycarbide. After 1 minute sulfurization, we can see here, you can see 2 rings here in the electron diffraction pattern, right? So these 2 rings belong to 2 phases of molycarbide. One is the alpha molycarbide, that was the starting material, and the other one is the gamma prime molycarbide. So which is gamma prime is a strain, not very common phase of molycarbide. So we can see these 2 concentric rings. And we can see this contrast so in here we have a combination of gamma prime and alpha molycarbide. So what we think is happening is that for some reason the sulfur is really going in there in between, but it's changing the carbide, but it's into a high strain carbide. After 5 minutes, we can start seeing the molysulfide here, layers here, but we can also see few layers in between. And in the electron diffraction, we can see three rings. So one of the rings belongs to the molysulfide, the other ring belongs to the gamma prime molycarbide, and the third one belongs to the alpha molycarbide. So we can see the three phases of the three different materials that we have there. Then after 20 minutes, when things are more thermalized, we have molysulfide and gamma molycarbide. And then here we just go back to the three rings. But then you transform from alpha molycarbide to gamma molycarbide, which is not the gamma prime. So we have to go to gamma prime to gamma molycarbide. So this is what we did, and we measured the. So this is just to show you the degree of, the molysulfide. We put it in different colors. You can have molysulfide layers now creating, intercalating, but you have molycarbide, gamma prime and gamma molycarbide. And we have here mainly gamma molycarbide, a few gamma prime, and then mostly gamma molycarbide. So this is what we have done. So we have done cross sections, we have done EM at different levels. And this is the TM of the same plates we measure the transport. So then we measure the transport, then we do the TM, the cross section. So this is
the laterally is not a single crystal. Probably not.
no, laterally it's a single crystal. Okay. So after the reaction, after reaction, it's in this regime it's not perfect. I mean, you started with a single crystal, and then this is.
Do you know what is a lateral crystal inside? So I guess that it's a vertically also it's a kind of different period. Let's go to the kind of 20 minutes of the sublimation.
Yeah.
So you have the molybdenum.
Yeah.
But this is not the large scale single crystal of molybdenum. Oh, I guess there.
No, there are some patches. Yeah, there are some patches.
Do you know what is the size of the patch?
They go along. I mean, if you do it, I mean, you go across along this. You follow them quite along region, and then sometimes you see an interface.
Yes, something like the range of the 100 nanometer, micron.
No, I think it's from 100 nanometers to micron. Yeah. After 5 minutes. Yeah. Then one of the things. So it was the mechanism. So we can see that. This is the carbide phase, and this is the molysulfide. So we can see stacking faults, and this is what we think. You can see the changing contrast here. You can see the H2S. I think it's traveling or is reacting very fast across along these stacking faults, and it happens from the edges. So it happens from the edges at different paces, but it starts with one layer, but it goes all the way through, because you have stacking folders. So that's what we think it's happening with the mechanism. And then we can do we can look a little bit at the interfaces of the different phases, and then we can correlate sulfides with the carbides. We can just work that out. But then what is interesting is that we did measurements of superconductivity. I mean, alpha molycarbide superconductor, it's a very sharp transition. So the crystal is nice, it's for around 4 Kelvin, and this is the different magnetic fields. And so one thing that we saw is that after 1 minute, then the transition was close to 7 Kelvin, and it was still superconductor. It didn't go all the way to 0, but it went down, right? So we have a transition. And 5 minutes was still around 6 Kelvin, and then 20 minutes it was still metallic, and up to 2 Kelvin we couldn't see a superconducting transition. But I think that might happen at even lower temperatures. Maybe that what will happen. So, but you have this is a good metal as well. So that we have. So this is so some of the explanations was that why it's happening. I think the strain and having these very metastable phases trapped and stabilized might provide this this increase in the superconducting transition. So local density of states, some calculations show that when you have these interfaces like these ones, you have states at the Fermi level or close to the Fermi level at those interfaces. But one thing is that even the moly sulfide next to the moly carbide is strained as well. So there are different things happening there. And this is the mechanism. So basically you have stacking faults, you have sulfur that goes through and you start creating the gamma prime moly carbide, which stabilizes into gamma moly carbide. But one thing that is very important is the alpha moly carbide was transformed into gamma moly carbide. Again, moly carbides, it's a ceramic, sort of, it's a metallic, there are metals and they are superconductive. And they are very hard. So these are interesting. So some of the things that we are doing right now, just to show you, is we are growing tungsten carbide, tungsten to carbide, and then we have these flakes, and yeah, we're trying to sulfurize, or we can try to do other things with them, like contacts. The work function of moly carbide, moly 2, is 4.3 electron volts.
So that's a low.
Yeah. Yeah, I just want to. So. Okay, so these are the ones that we can make, and again, and this is just, and this can be controlled. It's a few nanometers, or it could be usually from 20 nanometers, 20 nanometers, all the way to 7 in thickness, right? Okay, so I think I just yeah, I think it's almost time. So I think this is another work that we are doing right now, so related to boron nitride, and by cryomilling we're introducing defects into boron nitride, so vacancy, extended vacancies. So cryomilling is that you put your powder into liquid nitrogen, and you have an impactor, you start shaking it, and you start sort of milling, but in a liquid nitrogen atmosphere. So there's no other type of reaction that can happen during the milling process. And when you take it out, basically, I mean, the liquid nitrogen evaporates. It's what we found is this boron nitride that has lots of vacancies is very reactive, in a way that when you put it in contact with a salt, like silver nitrate, it becomes brown. So it's sort of, and usually boron nitride is not reactive. So here we're making boron nitride reactive, and we can basically reduce different metal nanoparticles. But what is more important, we have single atoms of platinum really embedded into boron nitride, right? So, and we have small clusters, but I think these are single metal atoms. Platinum are very interesting, and we have this. So we have done XAFs, and we have really made sure that this is just single atoms, that there are single atoms in the lattice. So this could be interesting. We're trying to see some other things, but I strongly believe that boron nitride is a very interesting system to keep studying it. And in this way, we're making boron nitride reactive. It's usually boron nitride is an inert material, but you can do a little bit of localized chemistry, because you have these vacancies that provide basically what happens is that this is the reduction potentials of the metals, and these are the Fermi levels of different defective boron nitrides that you can change, and these are the ones that would reduce the metal salts into metals. But also these vacancies are important for single photon emission and things like that. Now the issue is, can you control the defects and you have one specific defect, so you know what you have, and I think that's the challenge in the future. So I think with that, I hope I gave you a big overview of defects in 2D materials, a little bit of the carbides, and I would like to thank my sponsors and you for your attention, and people that are joined as well by Zoom. Thanks.
Then it covers very wide range of this material synthesis and characterizations. There's a lot of questions for the estimate. Let me start with the one that the last part of this quite willing that you just can put as a plate into a liquid nitrogen.
Yeah.
Or something, or you just
Yeah, there's an impactor. It's an impactor of usually it could be a polymer and you just impacting.
How do you impact it? It's only
No, it's just you move it like that. You just
you have some mechanical.
yeah, mechanical. So it's like by shaking
Shake it
with liquid nitrogen. So imagine it's like making a
with
cocktail.
some mixtures of polymer just shake. And
Yeah, that's it. And you are in an inert atmosphere, which is liquid nitrogen. So there's no other, compound that
But
could
then
react.
how do you incorporate this metal ions in?
And once you take it out, it's a white powder,
Yeah.
and then you just put the silver nitrate. You put a solution of silver nitrate and just starts bubbling like this. And then the suspension becomes brown. So that means that you're making silver nanoparticles.
I see.
So, but you can do it with copper, with iron, with different things.
Okay. All right.
You mentioned for the high doping vanadium dope sulfide,
Yeah.
you see these like clusters of
Yeah.
vanadium. Does that mean you see clusters of like ferromagnetic and ferromagnetic domains?
No, that's more uniform across the triangle. Yeah, but in principle, yeah, that's a good question. What happens if we do it under the conditions that you have hexagonal shapes, right? So the vanadium atoms will go, so that you would have ferromagnetic and non-ferromagnetic systems. You can solve that, yeah. You can have different ones. I mean, the only thing that it's the average distance between the vanadium.
I think that we have some questions from the Zoom audience as well. I think, Emily, can you actually read that questions for us?
Yes, we have two online questions from Tae-hee Kim. First one is, how could we control the concentration and location of vacancies in these 2D ML systems?
That's a good question. Usually it's through the synthesis, right? So by CVD, depending if you are using a low, for example, for the hexagonal islands, we use a low sulfur concentration, and that what happens is that we have also several sulfur monovacancies, right? So the way to when you have sulfur monovacancies, the way to anneal those is to use H2S, right? So that's to make it more perfect. But to control it is just if you carefully control the amount of sulfur that you put in the system, that would be. But again, it's the location. It's what is more complicated. I showed a way that when you have the hexagonal island, you can put atoms in specific phases of the hexagons, and that's sort of control that you have, but of course not the perfect control. Yeah.
Okay, thank you. And then the second question is, in the case of vacancy-free 2D WS2 ML, the dopant would be found at which site, W or S?
The vacancies were found at the yeah. Sorry.
But dopant, I think when you put the dopants, whether that will be substitute tungsten or so.
When you put dopants, well, there are different things that can happen. When you put dopants, sometimes you can have a vacancy, sulfur vacancy metal dopant pair. So you can have vanadium vacancy pairs. So next to the vanadium, there's a mono vacancy. So that's one thing. In some cases, depending on the size of the dopant, you can have only the dopant and no vacancy. But I don't know if that answers the question. But and they're usually the vacancies, the vacancy free are happening usually on the tungsten terminated edges.
Okay.
Thank
Any
you.
other-
No other questions online.
Right, let's thank the speaker once more then.
Yeah, thank you.
Thank you very much. That's the end of the Zoom session. It's always not easy to hybrid.
No,